So good afternoon, everybody, and welcome to our DaSSWeb Data Science and Statistics webinar series. Today, we have the great pleasure of welcoming Aurea Grané. She is full professor of statistics at Universidad Carlos III de Madrid in Spain. Aurea holds a PhD in mathematics from the University of Barcelona, and since then her scientific contributions are within the field of data science, developing robust statistic learning techniques based on the notion of distance between objects for visualization, prediction, classification of large and heterogeneous multivariate data sets. She currently coordinates the Statistical Data Science Research Group at Carlos III University in Madrid, as well as the Working Group on Multivariate Analysis and Classification of the Spanish Society of Statistics and Operations Research. Today, Aurea will present us her recent work on robust distances for mixed-type data. Dear Aurea, thank you very much for having accepted our invitation. We are very much looking forward to hearing about your recent work. The floor is yours.
Many thanks, Paula. Many thanks for your kind invitation and your kind introduction. Okay, so I'm going to present the recent work on robust distances for mixed-type data. Indeed, I'm going to talk about two or three works that we are more or less doing just now. So I'm going to start. Okay, so I prepared this talk. I have been a lot of days preparing the talk because I want to do just a revision a revision of the work that we started a long time ago and what are the things that are doing today. So I will start with some motivation. Then we will see a technique that is very useful to design distances for mixed-type data. After, I will talk about two clustering algorithms that we are developing just now for large data sets of mixed-type data and using these metrics, these distances that we have also developed. And finally, I will try to illustrate one of the methodologies in a recent application that has to do with real data. And we are interested in determining different mental health and well-being profiles in others all across the European Union. Okay, so let's go. Okay, so the motivation is this one, as you may know. In the nowadays data sets, they are more complex than ever. So in data sets, in today's data sets, we can find different types of information. So we can find quantitative data, qualitative variables. Also, we can find textual data, functional data, and so on. So I'm going to focus for this talk just on quantitative and qualitative variables. That is what we said more or less the mixed-type data. We call mixed-type data this kind of information coming from quantitative and qualitative variables. So challenges arise when we want to cluster in this kind of data and when there is also other things like an underlying correlation structure, redundancy in the variables, and also probably outlying units. So this is a real challenge to cluster this kind of mixed-type data. Trying to find a distance that is able to incorporate all the characteristics of the data. So a common approach when working with mixed-type data and clustering mixed-type data is to start by computing a distance that can work with these different variables of different nature. So the classical distance to work with is Gower distance. And once we have computed the Gower distance between units, a common approach is to, after computing the distance, to obtain a Euclidean representation, that is a representation of the data in orthogonal axes. And then once we have this representation, we want to cluster the data in that representation. And so since the axes are orthogonal, then we can apply classical clustering procedures like k-means or k-medians. Okay. Other approaches try to skip this Euclidean representation and work directly with the metrics of distances. So this is the case for k-medoids, that once we have computed Gower distance, we can apply k-medoids directly to the distance matrix. Okay. In any case, both strategies can lead to suboptimal results, mainly because classical Gower distance is not a robust distance, and it is not able to incorporate redundancy among variables. This comes because Gower distance inherits the same drawbacks as Manhattan distance. So Gower distance, is a hybrid distance that is composed by 3 different distances. So it uses L1 distance or Manhattan distance for quantitative variables. Then it uses the distance associated to Jacquard similarity coefficient for binary variables, and for the multi-class variables, it uses the Hamming distance. So since the L1 distance, that is Manhattan distance, is not robust for quantitative variables, and it is unable to incorporate the correlation structure of the data, so the same happens to Gower distance. Okay, so this is one of the problems of using classical Gower distance. Another problem arises when we use k-medoids in these strategies and when the sample size is very, very large. So k-medoids can be computationally infeasible for moderate large sample sizes. Okay, so the main goals of these works or this presentation is to, the main goals of the work is to develop a package that contains all these distances that we have been for a long time working with. So they are new distances. Some of them are robust, others are not, but they are designed especially for mixed type data, and they are able to deal with redundancy and outlying units. Okay, so this is a Python package that is already available. It is called PyDistances, and that was one of the goals of our work. Another goal is, and this is in the one that we are working nowadays, so is to develop a computationally efficient algorithm, clustering algorithm for these large data sets that is able to work with the distances that we have developed. This is another package that is, by now, it is ongoing work still. It is called fast k-medoids, and probably we have some modifications in it. Okay, another goal, an important goal, of course, is to check and to evaluate this new package. So the performance of these algorithms that the package implements. So we want to evaluate the performance of these 2 algorithms through an extensive computational simulation study, and we want to compare them to a wide range of existing alternatives, so competitors. Okay, so I will show in this presentation one of these computational experiments, that is the comparison with 15 well-known alternatives. Okay. And finally, we want to, because the main motivation was to work with large data sets, complex data sets that contain different kinds of variables of different nature. So I will show also the application, that is to create profiles of older adults regarding their emotional well-being, and these older adults live in the European Union. So the data comes from the Survey of Health, Aging and Retirement in Europe, and I will show just this is an ongoing work, and I can show just a brief summary of it. Okay, so to motivate, let's look at the data set. So when we talk of mixed type data, so this is an example of mixed type data that comes from the Survey of Health, Aging and Retirement in Europe. It's a large macro survey, very large. These are the letters in English, so the abbreviation in English. It's called sometimes SHARE, the SHARE project. You can Google SHARE project and you will find plenty of data and plenty of information. Okay, so it is a very rich panel database of individuals aged 50 or over in the 26 European countries plus Israel. For the application that I'm going to show, we will work with the latest wave, that is wave 9, that was collected between 2021 and 2022. We have also worked with previous waves and have other studies regarding wave 6, 7, and 8. But now today I'm going to talk only about this part. Okay, so from this wave, this macro survey, so we built our final data set. So since we were interested in looking for mental health and quality of life in older adults, we took this information from around 80 variables of mixed type, And from these 80 variables, we built indicators, each of which focus in an item of interest. For example, we have an indicator that looks at depression, that is based in the Euro depression scale. Another indicator looks for lack of quality of life in the older age, or loneliness, social integration and connectedness, and also general well-being. So we have 5 indicators built from 80 variables of mixed type using a methodology that we used a long time ago also. Okay, apart from these quantitative variables, we also include in the dataset other variables that have to do with loss of personal autonomy, so something that has to do with mobility limitations, the number of chronic diseases, if the person has limitations regarding activities of daily living or the instrumental activities of daily living, or also physical inactivity or some limitations with activity. Apart from this, we also consider some socio-demographic information regarding gender, marital status, if they live in a nursing home or not, the age group, the education level, and who is the first person that they can count with. Okay, so with all this information, we have variables of different natures, so quantitative variables, binary variables, and also multi-class variables. And with all this information, we built our final data set. And the question is, how can we consider all this information together in order to get different profiles of mental health and quality of life in the European Union along in this way? So the idea is to incorporate all these characteristics in the metric. So consider a metric. The idea is to build a metric that can integrate the different characteristics of the data, also the underlying correlation structure of the data and the probably outlying units. Okay, so I will start by talking of this method that is used to build the metric. The method is called related metric scaling, ReLMS. Okay, it is a very general technique that was developed a long time ago by Quadras and Fortiana. And we start to use it 10 years ago, more or less, to design metrics or distances for mixed type data. Okay, since then, we have used this methodology to visualize mixed type data, also to cluster weighted mixed type data. This is another possibility of more complexity in the data set when each individual in the data is associated to a weight that indicates the percentage or the proportion of the population that this individual that has been surveyed represents. So this is the case also for share. So share is a weighted mixed type data set. Okay. Also, we have used this methodology to detect multivariate outlying units and to robustify distance-based predictive models. Okay. So going to ReLMS, so related metric scaling. So imagine that there are not many formulas in the presentation, just a little. Okay. So imagine that we have our data set X, and that we are able to split the data set in several distance matrices according to its type of measure or its type of variable. Also, we can split it in different sources of information. Yeah, we will see. Okay, so all the matrices are measured on units, and they can have different number of variables. So in this presentation, for example, m is equal to 3. So we will have 3 matrices, one for quantitative variables, another for binary, and another one for multi-class variables. So as I told before, so ReLMS, related metric scaling, is a very general procedure that can be applied to any type of variable or source of information, so functional data, textual images, manifolds, or whatever you can imagine, provided that you are able to measure a distance function, you are able to compute a distance function between units, okay? So the mathematical proofs, you can find it in these references that are at the end of the presentation. Okay. So this is related metric scaling. You can do it in 6 steps, let's say. So the first step is to split the distance matrix in several distance matrices. To split the data matrix in several data matrices regarding each type of variable. Next, for each matrix xk, so we consider a proper distance measure between units according to the characteristics of the data that we want to consider. And from this, we compute the matrix of a square pairwise distances. So for each matrix xk, we select a measure, a distance measure, and we compute the matrix of square pairwise distances. Okay. So this matrix of square pairwise distances. So we have to standardize this conveniently using a concept that also was introduced by Quadras and Fortiana in 1995, that is called geometric variability, and this standardization has to do because in a forward step, we are going to combine all distance matrices and we want them to be commensurate. This is in Gower's, classical Gower's formula. This standardization was done in another way. But here we are doing it using geometric variability. So here you have the formula of geometric variability. It's a kind of mean between all the distances included in the matrix. Okay, so once we have our matrix of square distances, for each of them we compute the gram matrix, and next we have to check that all the gram matrices are, so we have to check that the configurations are Euclidean. So we have to check for Euclideanity, that is all the gram matrices must be positive semi-defined. This is an important restriction, but it is convenient to do this checking because it avoids to introduce imaginary dimensions in the metric, in the final metric. So sometimes they are not positive defined, it depends, but if they are not, we can apply a slight transformation to delta K, so to the matrix of square distances, and then get that the gram matrix is positive semi-defined. Okay. In general, we always apply the less restrictive transformation that is called additive. It's an additive transformation. You just sum a quantity in all the elements outside the diagonal of delta K, so that the final gram matrix is positive semi-defined. Okay, so you distort a little the matrix, but you don't lose the pre-ordering. Okay, finally, once we have all the gram matrices for all our different kinds of variables, we combine all the gram matrices and get the joint gram matrix. This is in the formula of Relemez. So formula 2 is the formula of Relemez. So in the first part, we add all the gram matrices, considering the different types of variables, and the second part of the formula, you subtract all the interactions between them. So, okay, so in the second part, as you can see, there is this exponent 1/2, that is the square root of each of the gram matrices. So to compute this formula, you need to take the square root of all the gram matrices. So you have to compute the singular value decomposition of all these gram matrices, and these gram matrices are n by n. So if the dimension, if the sample size is large, this part can be computationally expensive. Okay. Okay. Finally, imagine that our job is not computationally expensive, so we get our matrix G, and then to recover the distance, we apply this formula here, and we get the final matrix of square distances. So if we need the distances, but not in squares, so just we have to take the square root of the elements inside this delta. Okay, so this first part, yes, the first part of formula 2, so here it says, so the first part, the first addend of formula 2 is what we call generalized Gower distance. So this first part, because it mimics, so it reminds us the classical Gower distance, where all the different distances considered for a different type of variables are added. So this first part tries to mimic Gower's classical Gower's distance, and the second part is the one that is responsible for discarding redundant information. Okay, and it can be computationally expensive. This is the reason why we defined in a previous work. We define what we call generalized Gower distance by taking only the first part of this related metric scaling formula. So taking only the sum of all the gram matrices involved, which is equivalent to taking the sum of all the matrix of square distances involved. This is what we call generalized Gower distance. Okay, and this is the one that we are going to evaluate in the next slides. Okay, so the joint distances for mixed type data can be obtained either, so our proposal is to obtain them either by computing related metric scaling, so the whole formula 2, or just the first part of formula 2, that is what we call generalized Gower distance. In any case, we have to combine, we have to choose a distance for numerical data, a distance for binary data, and a distance for multi-class data. And trying to mimic or inspired by the works of Gower, we, in case of binary and multi-class, in case of multi-class, we only include Hamming distance, which is the same that considers Gower distance. In the case of binary, we consider two possibilities. Classical Gower uses Jacquard, so we use Jacquard, and also we add Sokol and Michener because they are the most well-known similarity coefficients. Okay, and in the case of numerical data, there is several possibilities, and we are particularly interested in the robust estimation of Mahalanobis distance, and here we propose 3 methods to obtain this robust Mahalanobis. Of course, there are other methods. These are very, very naive methods, let's say, to obtain a robust Mahalanobis distance. All these possibilities are included in the Python package, and probably we will include others. But by now, these are the possibilities. Okay. So our recommendations: in the presence of underlying correlation structure or when there are outlying units in the data set, all the combinations must include, well, this is our recommendation. We recommend that all the combinations include a robust Mahalanobis distance, okay? And we recommend this because in previous works, we have compared generalized Gower distance with robust Mahalanobis to classical Gower distance, and we get more stability and robustness in the MDS, in the multidimensional scaling representations. We get more stability in clustering results, and we get more efficiency in distance-based predictive models. So this generalized Gower distance is an extension somehow of Gower distance and when you use a robust Mahalanobis for quantitative data, you can take into account the correlation structure of the data, and you can also take into account the outlying units. Okay, so now that we know to compute a distance for mixed type data, so now we can go to see some clustering algorithms, some proposals for clustering data sets of mixed type data, so large data sets of mixed type data. Here are 2 proposals, so it's fast k-medoids and Q-fold fast k-medoids. And the idea is to use them in combination with the distances that are especially designed for mixed type data. And this is part of a PhD thesis of a student, and it is, of course, an ongoing work. Okay, so the first of the algorithms is called fast k-medoids. So imagine that we have our data matrix X corresponding to our variables that we have measured in a set of n units, and we are able to compute the distance between units, probably with one of the distances that we have seen. Okay, so the fast k-medoids algorithms has 3 steps. In the first step, we partition the data set into sets, one of the selected units and another one with the not selected unit, so a set and the complementary of it, okay? And in the cluster step, we apply classical k-medoids, so the partition is done at random, okay? And we have the selected set, selected at random, and the ones that are not selected are included in this complementary of S, okay? So in the cluster step, we apply k-medoids, classic k-medoids to the set of selected units and get the medoids. And in the assignment step, we assign the not selected units to their nearest medoid, okay? So this is as easy as it seems. So the key parameters of these algorithms are, of course, the distance, the number of medoids, and the number of selected units. Okay, so we have seen that our previous algorithms, so fast k-medoids, can lose accuracy as the sample size increases, and for that reason, we propose a hierarchical strategy that we call Q-fold fast k-medoids. So in Q-fold fast k-medoids, we start by splitting the data set in Q disjoint folds, and for each fold, we apply fast k-medoids algorithm, so the previous one, to get the medoids. So in the second step, at the end of the second step, all the units are assigned to a cluster, and all the units are associated to a medoid. Okay. So in the first step, we join all together all the medoids that we have found in all of the folds. So we consider all the medoids of all the folds, and construct and build this medoid matrix. Okay. And in the step 4, we apply fast k-medoids to the medoid matrix. So finally, we assign the individual. So in the step 4, when we have applied fast k-medoids to the medoid matrix, we obtain the final clusters. Okay, so the final clusters are obtained in step 4. And finally, we assign each unit to the final cluster that contains the unit's medoid, because the medoids of the units are classified here in one of these final clusters. Okay, so the key parameters here are the same as before, and also the number of folds. So these are the proposals that we are going to evaluate in different computational experiments. So these algorithms are implemented in this Python package that is called FastK-Medoids, and we are going to evaluate them using generalized Gower distance. So we are going to build different generalized Gower distances. So a distance, let's say a distance of the family of generalized Gower, using distance for quantitative data, one of these, Jakarta, Sokal, and Michener for binary data, and Hamming for multi-class, categorical multi-class. We are going to evaluate also, to evaluate the goodness of the partitions, we are going to consider the accuracy, the adjusted run index, and also the computation time. Okay. And here are some of the scenarios that we have considered. So all the data sets contain variables of mixed type. So we have 4 numerical variables, 2 binary and 2 multi-class. All the data sets contain this structure, but they differ in the correlation structures. So there are data sets with more correlation and others with less correlation. And also the proportion of outlying units is different in the different data sets. The number of true clusters is known in all the scenarios, and the data size, so the sample size, goes from 35,000 to 1 million units. Okay, so there are large and very large data sets. There are some with outliers and 2 data sets with no outliers. Okay, so I'm going to show you one of these computational experiments. So indeed in the paper that, this is at the end with the references, so you can find the different computational experiments that we did. We start by doing a comparison between K-Medoids and FastK-Medoids, just to see if the accuracy and was more or less the same, and the computing time was less with FastK-Medoids. Also, we check the stability of FastK-Medoids in terms of accuracy and in terms of the adjusted run index. We also study the accuracy and computation time for FastK-Medoids and Q4 FastK-Medoids. And finally, we did an empirical comparison to other competitors. And this is the part that I'm going to show you here. Okay, so these are the alternatives. So 15 alternatives that are implemented in scikit-learn and scikit-learn extra Python packages. And we are going to compare FastK-Medoids and Q4 FastK-Medoids using generalized Gower with all this. Okay, so here are some of the results for the first data set. So I know the size of the fonts is very small, but just look at the colors. So in purple color, we have the methods regarding FastK-Medoids. In green color, there are the methods regarding Q4 FastK-Medoids. And then in black color, there are the competitors. And in red color, also some competitors, but they turn to be invisible for this sample size. So in the first plot, let's say the first bar chart, has to do with the accuracy. The second one with the adjusted run index, and the last one is the computing time. Okay, so here is one possibility. Then, what happens is that as we increase, before going to the others. So another thing that we did is to try to visualize the clusterings, because here you have some measures just to know the accuracy, the adjusted run index, but we don't know what happens with the outliers and so on. So each data set contains outliers, and we want to see where the methods fail. So what we do is to compare the clustering visualization using multidimensional scaling. In this, now in the plots that appear in the slide, we use generalized Gower distance with robust Mahalanobis or inserialized Sokal and Hamming. So a generalized Gower distance built from a Mahalanobis distance, Sokal and Michener for the binary, and Hamming for for the multi-class. In the top panels, we have in first place the true groups, so the real groups, true groups. Then in the middle, so we have the fast gamedoids, and in the last one, we have the Q-fold fast gamedoids. The panels in the bottom show the competitors, so the best competitors. Depicted by triangles appear the outlying units, and depicted in points are the units that are not outliers. Okay, so what we can see is that looking at the competitors, for example, so the true groups are 4 groups, and there are outlying units in each of the groups. So what we can see is that the competitors fail in identifying the groups correctly, so the true groups are not recovered. And what all the competitors do is to identify the outlying units as a new group, which is not the case. Our proposal, so fast gamedoids and Q-fold fast gamedoids, reflect the structure, the group structure, or are able to recover the group structure and also to identify the outlying units. Okay, so we did this kind of representations for all the simulations, okay, and this is one of them. Okay, what we can see regarding the different scenarios is that as we increase the sample size, so fast gamedoids, start to go worse, and Q-fold fast gamedoids starts to go better. Okay. This is why we apply this hierarchical strategy. So as the sample size increases, this is what happens. Okay. Finally, if we go to the 1 million, so on top you have the green colors, and fast gamedoids goes worse. Okay. So here, in the case that there are no outliers in the data, so of course, competitor methods do a better job than us. When there are no outliers, so when the sample size is large and there are no outliers, LADK means is the best one, of course. But probably this is not. What also we can see is that there are some competitors that are not feasible for such large data sets. Okay. But what happens when we include more outliers in the data and more correlation structure? So when this happens, these competitors that were on top are not on top anymore. So when there are more outliers in the data and more underlying correlation structure, these methods are not able to incorporate or to recover the clusters. Okay, well, this is the last example of the visualization for this final data set, where again the same happens. So outlying units are identified by competitors as different groups, and the clusters, the cluster structure is not recovered by them. Okay, so I can show you part of the ongoing work with Irene Albarrán and the PhD student. Well, this is the application. So going back to the data, our interest was to study mental health and well-being in older adults and to obtain different profiles across Europe. And for that reason, we take the wave 9 of the SHARE project, so the Survey of Health, Aging and Retirement in Europe, from 80, I remember this, so from 80 mixed type variables, we built 5 indicators that focus on a particular issue of interest, so depression, lack of quality of life, loneliness, social integration and connectedness, so the networks of the people, and general well-being. Okay, and then we also include other variables that are related to the lack of quality of life and so on. So loss of personal autonomy, mobility limitations, chronic diseases, limitations regarding activities of daily living and instrumental activities of daily living, physical inactivity, and limitations with activities. And also some sociodemographic information of all individuals, so gender, marital status, if they live in a nursing home, the age group, the education level, and the first person that they can count with. Apart from these variables, there is also the weight of the individual. So each individual is associated to a weight that represents the percentage of the population, of the European population that the individual represents. Okay, so we have 40,000 units, 40,000 units that represent more than 180 million age Europeans or individuals in the European Union, okay? And there are indeed 17 variables of mixed type. Here with this heat map, I just want to show you that the correlation structure of the quantitative variables. So indeed there are variables that are moderately correlated. Okay, so this is not the identity metric, so we cannot apply distances that do not take into account the correlation structure of the data. Okay, and this is why we are going to consider generalized Gower distance with a robust Mahalanobis for quantitative data, a Hamming distance for multi-class categorical, and the distance associated to the Jacquard similarity coefficient, trying to mimic Gower's classical Gower's distance. In this case, we took, so we applied fast k-medoids, and we took k equal 5 because it was the one with best silhouette results and also a trade-off between the best silhouette results and the interpretability of the clusters. Well, here there are some, so here is the distribution of the mental health and quality of life indicators regarding several variables, so regarding several qualitative variables, so by gender, age group, physical inactivity, and we can see differences regarding age, for example, age group. So in the age, from 80, so individuals age 80 or more, there are differences. So differences in these indicators. Also in physical inactivity, also in the ones that have more than one limitations in activities of daily living, also in the instrumental activities of daily living, and yes, and there are also some differences can be observed in these indicators regarding if the person lives in a nursing home or not. Okay, so we applied fast k-medoids to this mixed type data set, and these are the profiles that we get. So these are the profiles. There are 3 female profiles, so 1, 3, and 5 are female profiles, and profile 2 is mainly a male profile. Profile 4 is not clear, so it's a quite mixed profile. Okay, so, well, the description of the profile has to do with all the variables included in the data set and the mode and the mean or the median of the quantitative indicators. Okay, so to describe these profiles. You can see here that we also consider the countries, so Western Europe, Northern Europe, Southern Europe, North and Eastern Europe. The country was not included in the data set. It was just used for interpretation after the clustering. Okay, so just focusing on 2 of these profiles, so profile 5 and profile 3. So profile 5 are the youngest Europeans, so mostly women. They are in good physical and mental conditions, so no chronic diseases, no ADL, no activities of daily living or instrumental activities of daily living limitations, with an active social network and a good quality of life. And the question is, we think that this group is an interesting group to track because we are interested in seeing if they will be able to maintain their good physical, mental, and social health as they will age. So what will happen with them in the future? This group of people, of young women that are in so good conditions. Because we don't, I think I am in this group, because we don't want to end as the women in profile 3. So profile 3 is the elderly people to be cared for. So they are the oldest Europeans living in residential care homes, mostly women with physical health problems. They have mobility and limitations of daily living and the instrumental activities of daily living, and they have several chronic diseases. So their basic needs are covered, but they feel depressed and they perceive their quality of life as poor. So this is why I think it's a problem in general in the southern Southern European Union. And we really do not want to finish to end like this. Okay, so just for interest, where is this profile mainly in the data set? So Spain is the top of the ranking. So 30% of these individuals are located in Spain. Or so, not 30%, so 30% of the people of Spain have this kind of profile. Well, you can see Israel, Croatia, Lithuania, Estonia, Italy, Bulgaria, Romania, Poland, so all Latvia, Hungary, Cyprus, and Switzerland, Greece have more than 20%, Malta is 20%. So more than 20% are in these countries. And of course, in the other way around, so you can find Sweden with a less proportion, Czech Republic, Netherlands, Denmark, Luxembourg, Finland, and so on. Okay, so this is all I want to talk. Well, we can see some conclusions, but it's just to repeat the same. So we have proposed two clustering algorithms based on distances, especially designed for mixed type data, are proposed and studied. We found that they are very effective, particularly when we use robust generalized cover distance for data sets with outliers. Competitors' methods fail in identifying outlying units and classify them as a new group. And in the case of big data, our methods are still best when outliers and moderate to high correlations are involved. And although the methods are not, our proposals are not the most computationally efficient, they are significantly more affordable than k-methods. So these are the conclusions regarding the methodology. And here are some references. Here is the last two has to do with the algorithms that we have proposed, that is a working paper. And the evaluation of generalized Gower distance is done in this other one, the second paper here, that is by now submitted to SORT. It's in second revision. And Pierre Legendre is helping us with all this, so it's quite motivating. And okay, so here I have put two links to the Python packages, so PyDistances and fast k-methods. And that's all that I wanted to talk. Thank you.